So I'm going to talk today about electrical safety, but through the other side of the lens, not from an engineering viewpoint, but rather from a medical perspective. And the starting point, I'd just like to highlight the fact that much of what's written and taught about electrical safety from the engineering viewpoint relates to the prevention of circuit overloads and fire, and not to the prevention of electrocution. Now, electricity as a form of energy remains a cornerstone of the modern world, and it's brought endless advantages, of course, to mankind, but it's come at some danger. So what I want to talk to you about today is what actually are the dangers from electricity. What are the effects of electricity when it gets in contact with the body, and what are the modes of injuries that can be suffered? I want to talk as well about what does it matter for us as radio amateurs? How are we affected in terms of that risk if we have an element of heart disease ourselves, or if somebody in the family does? What does it mean for us if we need to have a pacemaker? And what does it mean for us if we need to have one of the new implanted defibrillators put in? And if we've got time, I'm conscious of the time, but I'll try and dispel a few myths that there are about electrical dangers. Now, for completeness, we'll just talk a little bit about lightning first of all. This is a special case, but it's really beyond the scope of this talk, other than to say that about 90% of people who are actually hit by lightning survive. Lightning itself causes around about 10 deaths a year in Australia, so it's a very rare cause of death. And the majority of people who are killed from lightning are actually killed from falling branches or trees exploding that they're hiding underneath when they're struck by lightning, and not by the electricity itself. I'm going to differentiate and highlight the differences between direct and alternating current, because that's actually at the center of all of this. And I'm going to touch on the effects of radio frequencies when we come in contact with that as well. Now, the true risk of exposure to RF and microwaves is way too big a topic for this to be covered here today, but perhaps a topic for next year if we have a rematch. So first of all, can I ask the audience here, how many people here today have been electrocuted? Can I have a show of hands? Okay, there's almost half of the people in the room have put their hand up today. Okay, well, I'm happy to tell you that no one here in this room today has been electrocuted. No one. Okay? Because electrocution, by definition, is a mode of death. Electrocution means death by electricity. You can't survive it. If you're here, you've not been electrocuted. And it's a common mode of understanding, and even Wikipedia's got this wrong. So death is, by definition, an irreversible cessation of vital function, okay? It's a failure to revive or the end of life. It can't be survived. So what about the modes of injuries? What does electricity actually do? Now, in general terms, the mode of injury is determined by the magnitude of the exposure to an electric current. Now, at the lowest end of the spectrum, an electric current produces an unpleasant and a painful sensation, or an involuntary and often quite violent withdrawal response, just like touching a hot soldering iron. But that violent withdrawal can be serious enough to cause injury in its own right. And if you happen to get in contact with current when you're at the top of the ladder, then the fall itself can do more damage than the electricity itself. Now, larger flows of currents can cause muscle paralysis, and eventually they can stop your breathing, and that's not a good end to the day, I can tell you. And larger currents still can cause loss of consciousness or cause generalized convulsions. And at the very top end of the spectrum, electric currents can produce major burns or even blast or explosion type injuries in an industrial setting. But the malignant specter that haunts us all with electricity is the ability of electricity to cause a fatal cardiac arrest by inducing ventricular fibrillation, or VF. And you'll hear me talk a lot about VF today. And it can do this without leaving a single mark on the body. So discussion of electrocution is really about a discussion about ventricular fibrillation, VF. So how common is it? Well, here in Australia, we're a population of about 26 million people, and we have a death rate here of about 7%. So that means that we expect about 1.8 million deaths a year from all causes in Australia. Now, there's about 20 deaths a year from electrocution. And we know this because in Australia, as with all accidental deaths, there's a statutory reporting requirement to the coroner, so we know exactly how many people are affected. Now, 20 deaths, while being very tragic, is still a very, very rare cause of death indeed. In fact, that's a fraction of the number of who are killed in Australia by bee stings each year. Now, of those deaths that do occur, 2/3 of them occur in an industrial setting, and the remainder at home. Now, there's another term that gets bandied around, and that's this discussion about electric shock. Now, shock from a medical perspective has a very distinct and very clearly defined medical diagnosis with a specific meaning. Shock means that vital tissues in the body are not being perfused, they're not getting any blood flow, and the tissues die, and shock has a very high mortality. Now, there are many, many causes of shock. The commonest is probably from major hemorrhage after a road traffic accident, gunshot wounds, whatever. Shock can happen after anaphylaxis from whatever, a massive overrun of your allergic system, or it can happen with sepsis and overwhelming infection. But electricity is not one of those causes. From a medical perspective, there's no such thing as electric shock. Electricity is not a cause of shock. From a medical perspective, it's a lay term only that's ill-defined, much loved by the media, but it isn't really doesn't actually exist. So it's come to mean any sort of thing that happens if you come into contact with electricity. Anything from a static discharge when you touch the car door handle on a hot day, right up to something more serious. Anything, in fact, to do with electricity that doesn't actually cause a fatality. So what are the effects of electricity on the body? And there are 3 body systems where electricity can have an effect. We've got the brain and spinal cord and nervous system, the thinking bit, the bit of software that runs in the middle, the wetware. We've got the muscles that we control with impulses coming out, which allow us to move, and of course it's a two-way transceive process, there's sensation going in. And then we've got the heart. Now, it's a common misunderstanding that the brain, the muscles, and the heart operate like an electrical system in the body. And this isn't the case, in fact. Nerves are not wires or electrical conductors, and nerve impulses are not electrical signals per se. They're actually a biochemical process, not an electrical one. Transmission, for example, between one nerve and another, or between a nerve and a muscle, is achieved by releasing a substance into the gap or the synapse between the two. They're not actually in electrical contact at all. The reason it's important is that the biological process is not instantaneous. It takes time to happen. That being said, though, although this isn't an electrical process, all 3 of those tissues will produce an electrical signature when they're working, an electric signal that you can actually detect on the surface of the body. And further, all 3 of those tissues, so the central nervous system, the muscles, and the nerves, can all be stimulated by an electric current and actually mimic their normal function. Just to give you an idea, the beating heart produces an ECG, an electrocardiogram signal, on the surface of the heart of about 3 millivolts. Muscles contracting produce about 10 millivolts, and the brain, when it's clattering on as you're doing mental arithmetic, there's a signal of about 0.1 of a millivolt coming out. These are signals that you can detect on the surface of the body. So let's look at the effects of an increasing electric current through the body, and let's consider a current that's going from hand to hand. Now, at the low end of the spectrum, about 1 milliamp of AC is the threshold for sensation at the fingertips, and it's normally perceived as a tingle or a vibration. Now, you'll notice immediately that there is a massive difference between AC and DC in this regard, alternating current being far more stimulating. Now, at 10 milliamps, most people start to experience pain, and this is usually associated with a powerful involuntary withdrawal response, just like anything else that's painful. Not much higher than that, around 15 milliamps, AC current starts to cause direct stimulation of the muscles, and this is both unpleasant and painful. And depending on which muscle groups are involved, you might either be thrown off the current and break the circuit, or it may render you unable to let go. And these contractions can be powerful enough to break bones, shatter teeth, or even snap your spine. At 50 milliamps, you get generalized muscular paralysis, including the muscles that you need for breathing, so you go into a respiratory arrest. Not a good day. At the very high end of the spectrum, currents over an amp can start to cause thermal damage, or burns, in other words, to tissues both at the entry and exit points on the body and in the tissue in between. But again, highlighted in red here, there's the dangers of VF arrest. Now you can see that you can get fatal ventricular fibrillation at less than 1/10 of the current to cause a true electric burn, and this will cause a cardiac arrest. So, in reality, as I said, electrocution is about alternating current, and it's all about the phenomenon of VF, cardiac arrest. And this is the silent killer that can leave no mark on the body at all. It's a silent killer that can affect normal, healthy young hearts as quickly as the old, sick ones. Now, why is this so? Why does it happen? Why is AC so much more dangerous than DC in this regard? In fact, it's very difficult to determine how dangerous DC is, and it's really questionable whether direct current can even cause VF at all. So a couple more questions here for you in the audience. How many people got pacemakers here? Anybody got a pacemaker? A couple of hands gone up. And how many hearts have we got? Okay. Well, so we've got the human heart, a little characterized diagram. I'll run through this a bit. You don't all need a biology 101 course today. Now, the human heart weighs about the same as a carton of margarine. We have a resting heart rate of about 70 beats per minute, and a stroke volume, that's the amount of blood that's ejected with every beat, of about 70 mils. So if you do the maths on that, you find that the heart, when you're not doing too much, is pumping out about 5 liters of blood a minute. How long is a heart going to last you? Well, there's a myth that says that you're only given a certain number of heartbeats and you shouldn't go wasting them running around doing SOTA and up and down mountain peaks. In fact, there's no truth in that. But in reality, in a 70-year lifetime, your heart's going to beat about 2.5 billion times. So it's a pretty reliable bit of kit. In fact, it's going to last you a lifetime. Now, anatomically, we have one heart, and it lives in the left side of our chest, and as we said, its function is to pump the blood around all the organs of the body. But functionally, we actually have two hearts, two pumps, and they're connected in series. We've got a left heart that pumps blood around the main body at high pressure, and we've got a right heart that pumps blood through the lungs at low pressure, picks up oxygen, shoves it back into the left side, and round we go again. Now, these pumps are driven by muscle, and it's a mechanical and it's a pulsatile pump, and it runs as though it's running on a common shaft, so it's all synchronized to get an efficient operation. So here's a diagram of the heart, and I'm just going to highlight just a couple of structures here. So the heart's got 4 chambers. We've got a left and a right ventricle. They're the powerhouses. They're what actually do the pumping. And we've got a left and a right atria, which are the atria, the entrance halls. So these pre-prime the ventricles to beat. Now, if you could take one cell from a heart, just one muscle cell, and put it into a test tube with some saline in it at the right pH and temperature, that single cell will beat. Okay, it's designed to do that. Unlike our normal muscles that we're under control of, cardiac muscle cells will beat spontaneously. So they display this phenomenon of rhythmicity. If you take a big chunk of muscle cells from a human heart and do the same thing, they'll all still beat. Every single muscle cell will beat spontaneously, but they all synchronize to whichever cell is beating the fastest. Okay? So they display what's called synchronicity. The fastest cell in the block becomes the pacemaker. So in fact, we've all got pacemakers. We're all born with them. And transmission from one cell to another isn't instantaneous. It actually runs like a wave that floods from one side of the heart to the other. So in the normal cardiac cycle, contraction is actually initiated by a specialized little node up here in the top of the heart. We call it the SA node, or the sinoatrial node to give it its proper name, and it happens to be the bunch of cells that's got the fastest native rate. So all of the rest of the heart synchronizes to it. We've all got this pacemaker. That wave of contraction propagates over the top of the heart, squirts blood into the ventricles. Now the signal, the electrical activity that's going on, comes then through a specialized bundle of fibers down through the middle of the heart, but this gap here goes to another node. We call it the AV node, the atrioventricular node, and that works like a little biological delay line, if you will, and it just allows time for the mechanics to catch up, for the blood to flow. Now on the electrocardiogram, this is the 101 style picture of the cardiac, the electrical cardiac signal. Contraction of those first chambers of the atria, they produce this little green low voltage pulse here. We call it the P wave. It's not very imaginative, but it's called the P wave. After a delay, while it gets through the node, the ventricles then fire off, they contract, and that gives rise to this high voltage complex here called the QRS complex, even less imaginative. And that is the electric signature of the ventricles contracting. After that, all of the muscle cells in the heart go through a recovery, or a phase when they start to repolarize and get back to normal, and that gives this electrical signal called a T wave, P, QRS, T. You'll remember, that's not hard to remember. Now, in the normal cardiac rhythm, then we call it the sinus rhythm because it's driven by your normal sinus node. There's this regular progression, P, QRS, T, P, QRS, T, P, QRS, T, a steady and a regular rhythm, and that's where we normally all sit. Now, in ventricular fibrillation, this terrible rhythm that we can't survive, that normal coordinated contraction is lost. Now, the heart hasn't stopped. Every single cell in the heart's still beating, but it's doing it in a totally chaotic way, and it gives rise to an ECG that looks like this sawtooth down the bottom here. Okay, the heart, if you can see one, appears to be quivering like a bag of worms, but there's no blood being ejected, there's no circulation, there's no pulse. So ventricular fibrillation is what we call, it's an arrhythmia, and it's incompatible with life, and if it's not corrected urgently, it's rapidly fatal. VF arrest is common after heart attacks, for example, but it's also the arrhythmia caused by AC current exposure. And luckily, it can be reversed very quickly by defibrillation, but it does have to be immediate. And I'll explain what defibrillation does shortly. So electrocution is really about alternating current. Now, in the 1880s in the USA, there was a power struggle going on, literally. There was a commercial war of the currents playing out involving these three individuals that you see here on the screen. Now on the left, this is Thomas Edison. He was a prolific inventor and entrepreneur. Invented the light bulb, and he'd invested massive sums of capital to provide an electric system and electric lighting of major cities in the US. But all his systems were based around the generation of DC, of direct current. Now, the single major problem with DC is power loss during distribution. Simple I²hour power loss, but it's so severe that it means you have to generate the power where you're going to use it, or within a mile or so. In the center, this is Nikola Tesla. We know him from his radio research as well, and he was a former employee of Edison. And he had demonstrated the advantages of alternating power and actually invented himself three-phase or polyphase current to drive electric motors. Now, the single major advantage of AC is the simplicity of stepping up the voltage with transformers and allowing efficient transmission of power at high voltage with minimal power loss over long distances, and allows you to generate your power at a great distance from where you want it, so you can have a central location. On the right, this is George Westinghouse. He was the founder of the General Electric Corporation. He was funding Tesla's concepts for a much better and more efficient power system. And these three characters were locked in a major commercial and legal battles for the best part of 2 decades. Now, from a historical viewpoint, as Westinghouse started to gain traction with his AC power systems, there were a number of tragic deaths from electrocution from people coming in contact with the new current. Now, as part of his campaign for the retention of DC as the preferred system, Edison commenced a series of public campaign against his competitors to highlight the dangers of AC. And this campaign included public displays of the electrocution of dogs and horses and other animals using AC from one of Westinghouse's own generators. Edison even went as far as arranging the most bizarre public display of the electrocution of a circus elephant called Topsy, and he did this demonstration at the opening of a national exhibition in the US. And it got worse. To further his cause, Edison also proposed to Congress that AC electricity from a Westinghouse generator could be used for capital electrocution as a more humane alternative to hanging for the death penalty. And in 1889, William Kemmler, who was a convicted murderer, was executed by electrocution in one of Edison's electric chairs. Whoops, what happened there? Sorry about that. Now, Westinghouse subsequently sought a court order to prevent any of his generators ever being used in this way. But of course, the rest is history. The major advantages of AC over DC for efficient power generation and distribution inevitably led to commercial success, particularly as electrification of domestic and industrial properties was rolled out, not just for street lighting. Now, it would probably be all different today. I mean, there's been a resurgence in interest in DC power distribution because using inverter technology rather than transformers, it is now possible to efficiently convert DC to any voltage or type of current that you like, particularly with the expansion of solar power generation, for example. And DC distribution at high voltage gets around many of the problems of power factor correction, synchronization of generators, and also lower installation requirements because the peak voltage is substantially lower for the same power level. And of course, there's a significantly lower risk of electrocution. So VF from AC currents is the problem. So what are the factors that actually influence whether or not you go into a ventricular fibrillation if you get exposed? Now, the single most important factor, the first starting point, is the magnitude of the current itself, how much current flows. So it's the current, not the voltage, that's important. The next critical factor is the path that current takes, okay? And the reason for that is that the two factors of current and path, they determine what we call the current density in the heart muscle itself. Now, this is something you may not have come across, but current density describes the current flow per unit of cross-sectional area of the heart muscle, and this is the critical factor that determines whether it goes into fibrillation or not. Current flowing from hand to hand, for example, or directly through the chest wall produces very high current density, far higher than the identical current flowing, let's say, between hands and feet. And so the cardiac arrest risk is much higher. Next critical factor is the duration of the current flow, how long it flows for. Now, for 50 hertz exposure, VF is almost impossible or almost unknown if the current flows for less than about 20 milliseconds. This, of course, this is the target time for most of our current earth leakage protection devices. And if you do the math, you'll see that 20 milliseconds is actually the duration of one complete AC cycle. And there's actually the clue to the mechanism of VF itself. Now, the next critical factor is the frequency. Now, it's sadly ironic that the mammalian heart, and we are all mammals, is exquisitely sensitive to a narrow band of frequencies between 50 and 60 hertz. Okay? We could not possibly have chosen a worse frequency for our general power generation. So why did we? Why did we choose this frequency? Well, engineering. It's about generator design and shaft rotational speeds. It was chosen to optimize transformer efficiency and engine speeds, and once you've established a standard, it's very difficult to change it. Ironically also, sine wave current is again far worse than anything else. It's the worst of all for any given current density and duration. For example, pulsed electric energy at the same magnitude and frequency and duration has a much lower risk of inducing VF than sine wave. But there's another factor, and that is pure chance. Maybe better describe it as luck rather than chance. There are many examples of individuals being exposed to very high currents for dangerous periods of time, but who have survived. Now, there are lots of medical situations where we deliberately try to induce VF in patients. For example, if you've just had one of these implantable defibrillators put in your chest, before we wake you up from your anesthesia, you've got to have it checked. And the way we do that is that we pass some 50 hertz sine wave AC through the pacing wire and make the heart arrest, and then we see if the defibrillator charges up and fires. And sometimes it doesn't want to do that. I can tell you, it's very, very frustrating sometimes. Just doesn't want to stop. Now, there are lots of medical treatments and diagnostic procedures which involve the intentional exposure of the body to electric currents. Some use AC, some use DC, some use pulse, some use currents, alternating currents right up through the RF spectrum, right up to and including microwave. For example, diathermy systems, an electrosurgical system used to cut through healthy tissue to control bleeding and to intentionally destroy tumors, for example. These devices, they use 400 or 500 watts of RF, either at around 500 kcs or at 30 megs, the noise bands, the industrial, scientific, and ISM bands. And even when you use these directly inside the chest alongside the heart doesn't fibrillate because of the frequency. MRI scanners, I don't know how many of you have been in one of these. These are used to image internal organs without the use of X-rays. They involve the use of hundreds of watts of UHF being aimed into the body and placing you in an intense magnetic field. Again, no VF risk. ECT, electroconvulsive therapy, still a cornerstone of the management of depression and psychiatric illness even today. This involves the passage of several hundred milliamps of AC directly through the head, albeit under anesthesia, to induce a controlled convulsion. But that current is pulsed, not sinusoidal, no VF risk. Here's a couple of those machines. This is a diathermy machine used in a surgical operating theatre. These numbers here, this is watts. So the cutting diathermy uses the lower frequency, the 500 hertz stuff, and the coagulating diathermy uses the 30-odd meg stuff. Where heat's distributed, it depends on frequency, but doesn't cause VF. This is an ECT machine. Again, passes what should be very dangerous currents, doesn't cause cardiac arrest. And this little machine, this is a TENS machine, a transcutaneous electric nerve stimulator used for controlled pain by passing pulsed waves through the spinal cord. I'm rushing through it a bit because I know time's running. Now, this is a defibrillator, so let's talk about defibrillators. What does this actually do? Now, in simple terms, this is a device to resynchronize contraction of the heart that's in ventricular fibrillation. When I first qualified back in the 1980s, these devices were the size of a filing cabinet on casters, and they used to come in plugged into the mains electricity, and not everywhere had them. So we're going to deliver a dose of electricity to the heart somewhere between 50 and 360 joules through paddles like this applied directly across the heart. And what they do is they pass a very large pulse of DC directly through the heart, through the chest wall. This produces a very high current density in the heart, as you'd predict. And what it has to do, it has to capture the contraction of every single heart muscle cell. So it makes every single cell fire, contract together, then they all go into that recovery phase together, and hopefully at the end of it, they all come out in a normal sinus rhythm. And the early defibrillators, they were akin to a massive great flash gun. You had an inverter which charged up a 200 microfarad capacitor, and the operator, me, would fire the buttons to send that current through the chest. So energy stored in a capacitor, half CV squared. If you want to store 360 joules in 200 microfarads, 2 kV, 2000 volts. That's what used to come out of the paddles. Let's talk a bit about pacemakers. This is something else we want to know. Now, we've said we all have our own pacemaker, but if that fails, or if the conduction system in the heart fails, the impulses that are supposed to go to the ventricles and drive them to contract and pump the blood for you will also fail. And this is a medical condition called heart block. And when this happens, it's associated with a very, very low or absent heartbeat. And before the advent of pacemakers or artificial pacemakers, this was typically an end-of-life experience. We'll move on from there. Here's a picture of a very early pacemaker. This gentleman, this patient here on the side, he is actually pushing around his pacemaker. Okay, so this was a large device, again on a trolley. At least it would allow him to walk around a little bit. Plugged into the mains. So his whole life is as long as his power lead is. And the machines themselves, they produce a pulse of current, direct current, at a fixed rate through wires that were surgically implanted onto the surface of the heart and then brought out through the chest wall. So as well as being, as I say, being very large, they're powered by the mains. Now, after a number of power cuts and bad outcomes, shall we say, there was a push to try and create a totally wearable pacemaker. In 1957, Dr. Bakken, who I believe was a radio amateur himself, built this device. It was a totally wearable, self-contained external pacemaker, and the design he used to build it was actually of a metronome from a popular hoppy electronics magazine of the day. But these machines, you know, they made a huge difference. They allowed people to survive who otherwise weren't going to. They saved a large number of lives, but there's one fundamental flaw with these fixed-rate pacemakers, which had to be sorted out. Now, a normal pacemaker, when it works, is supposed to apply an electric pulse to mimic what the heart normally does. So you apply an electric pulse here where the P wave should have been, and it causes a normal contraction, the QRS complex. But if you inadvertently try and pulse and pace the heart when it's trying to recover, it'll go into VF. It's called an R on T phenomenon, and if your heart's got no conduction at all, it's not a problem, but if some of your native heartbeats are getting through, then they can conflict and your pacing beat can actually put you into a fatal situation. So the current pacemaker designs avoid this risk by both sensing and pacing down the same wire. And these wires are inserted onto the inside of the heart, not the outside. So in a demand pacemaker, which is what these are called, if the heart is beating, the pacemaker does nothing. But if for any reason the heart misses a beat, then the pacemaker drops a beat in, so the heart rate is maintained. And this is a photograph of one of the current generations of pacemakers, first introduced at the end of the 1950s. These were fully implantable devices. The current models now are powered by lithium iodine batteries and through pacing wires on the inside of the heart. The modern ones are electrically programmable from outside with an antenna, and they're about the size of a wristwatch now, a man's wristwatch. They cost about the same as a small family car, incidentally, to buy one of these and have one inserted. What does it mean for you then if you actually have to have one of these devices put in? Well, in fact, even as a radio ham where you're around RF fields, there's actually minimum risk with these of RF exposure. They're well designed, they're well filtered. Standard RF that we're likely to be exposed to is not going to do anything. You do have to be vigilant around electrical contact, although the risk is very small, because if the pacemaker detects electrical signals, it's going to assume that your heart is beating and it won't do anything. So if you're dependent totally on your pacemaker, it will stop and you will probably faint. The one thing that you have to be very careful of is about magnetic fields. Anybody who's had a pacemaker or knows, got anybody in the family knows this, you're not supposed to put magnets anywhere near them. And the reason for that is that they all come with a reed switch built into them. Now, the reason that reed switch is there is to allow people like me to switch them off. If there's for any reason that you have to turn the magnet, if you have to turn the pacemaker function off, we deliberately put a magnet over your pacemaker. For example, if you're going in for surgery and you need to use diathermy, the pacemaker will say, "The heart's beating, I won't," and the circulation will stop. And the surgeons might not notice, but believe me, it sharpens up my day fairly quickly when that happens. Of course, if you put the magnet on, the machine goes into its fixed rate, and it exposes you as a patient to the R-on-T phenomenon, which we were trying to avoid by putting demand pacing in the first place. But it's only ever done when you're under highly monitored conditions, so it's quite safe that that's done, and it's done routinely. But there are large magnetic fields in other places like MRI scanners and airport body scanners and magnetometers and things. So you do have to be very careful that you don't get any fixed magnetic fields near your pacemaker. Now, another medical revolution has been the development of these. These are fully implantable cardiac defibrillators, AICDs, like this one that's shown here. Looks for all the world like a pacemaker. And these are implanted into patients who are at a very high risk of VF cardiac arrest because of their own cardiac disease. They continuously monitor through the pacing wire for that characteristic sawtooth wave that we saw that tells them that the heart is fibrillating. And if that happens, then the defibrillator charges up like a flash gun and delivers a defibrillating pulse back down the pacing wire. Now, most AICDs also have the standard pacemaker functions as well. These guys come at the cost of a high-end BMW to get one of these implanted, just so you get some idea. They're thick end of 100 grand to have one of these. And like pacemakers, they also have a reed switch, which can be used by medical staff with a magnet under the right circumstances. But if you put a magnet on one of these, two things happen. First of all, it goes to a fixed rate like a pacemaker from before, and it also switches off the defibrillator function. So you've introduced the risk of R-on-T and then stopped you being protected from it. So it's very important, again, that you avoid that situation. This is done deliberately, again, during surgery or some diagnostic procedures where the current can be confused or misinterpreted by the defibrillator as being in ventricular fibrillation. Otherwise, it will fire. And that's not a very pleasant experience if you're awake. So if you have an AICD implanted, what does this mean for you? In general, AICDs give you a very wide protection against VF cardiac arrest, but contact with even low amplitude electric currents can potentially cause the defibrillator to fire. What's happened there? Excuse me a moment. So you have to have very high vigilance against any 50 hertz electrical contact or things like car ignition systems or anywhere where there's high voltage pulses. And you have to have very high vigilance against being exposed to fixed or alternating magnetic fields from transformers and the like. RF, risk very low indeed, but the other things that might be in the shack are a problem. So it's super important to avoid exposure to all of those magnetic fields at least. Two last things, two bits of medical advice for everybody. Every shack wall and every workshop should have a resus chart on the wall. Everyone should learn some basic CPR skills because evidence shows that your chance of surviving a cardiac arrest from whatever cause is determined by the time interval between the cardiac arrest occurring and when effective CPR is started. And we'd all wish that whoever's first to help us, if we have a cardiac arrest, knows some CPR. And finally, best bit of medical advice at all, get your radio club to raise some funds and get one of these. Now, this is a fully automatic external defibrillator, and they're found in many public spaces and buildings. They're easy to use without any medical training whatsoever. This one, for example, is on the wall of the Brisbane VHF group meeting venue. These guys save many lives every year, and one of them could be yours. Thank you.